There's your riveting intro to today's Kin 225 class for March 30th. Okay, we'll get to our lecture here. So first thing I have for you is a quick announcement. Just a reminder about your final exam. It'll be on the same day as the original scheduled exam, Saturday, April 25th. It'll be open book as per the university's policy for this time of the year. You'll be given, it's untimed, again, by the university's policy, so you'll have the entire day to complete it. It's going to be 120 multiple choice questions. You can see 30 questions from material before the midterm, 90 questions from material after the midterm. Your Lab 6 is due today, so try to get that in on the Blackboard system. And your Lab 7 is due next week, so April 6th. With regards to your next lab, Lab 7, you're going to have to determine the anaerobic threshold, probably from data that Vanessa and Doug are going to supply you. And these are some tips on how to plot your data to determine your anaerobic threshold. So you'll notice two variables here. There is ventilation that's plotted on the y-axis. And in this case, we've plotted VO2, your oxygen consumption, on the x-axis. Oxygen consumption during this type of test increases in a linear fashion. So this is a test that's done on a bike, and every couple of minutes, the intensity on the bike is increasing, so your workload is gradually increasing. Your oxygen consumption will increase in a linear fashion up to a certain point until you reach your maximal oxygen consumption. Your ventilation increases with oxygen consumption at first, and then ventilation will increase to a greater degree than oxygen consumption. So these dots represent your ventilation plotted against your oxygen consumption. And you can see the ventilation starts off kind of with a linear increase, and then it takes off, so it's non-linear. And then these are kind of garbage data points at the end of the test. So don't really look at these ones. So this is your typical test of progressive intensity and how your ventilation would change during that test of progressive intensity. To find the anaerobic threshold, it's the point at which your ventilation starts to increase dramatically. What I've done is I've drawn a linear line through these first set of data points, and then another line through that second set, and where those two lines intersect is your anaerobic threshold. So that's one way you can try to determine your anaerobic threshold. So this is for Lab 7. A second way, so I've taken other data and plotted it on this graph. So again, I have ventilation on the y-axis, and then on the x-axis, I simply have time during the test, and those would correspond to the seconds during the test. So keep in mind, during this test, a person is pedaling on the bike, and as time progresses, the workload on the bike becomes more and more difficult. So your ventilation, again, starts off to increase in a linear fashion with time, and then once you hit that anaerobic threshold, it starts to take off pretty much in a non-linear fashion. So to find the threshold, this is just a different way to find the threshold, is I've drawn a straight line as best as I can through those first initial data points. And then when the ventilation deviates from that linear straight line, that's the point at which you identify your anaerobic threshold. So hopefully Doug and Vanessa will send you some clean data. Sometimes it's difficult to find the anaerobic threshold. It can get messy sometimes. So for today's class, we're reviewing the glycemic index, and I've got some review questions on diabetes. And then I'm going to get into fat metabolism, fatty acids, metabolic pathways in muscle. Also going to cover liver and how fat's stored. And as I mentioned in the glucose section with regards to metabolic pathways, you'll see that we've already covered most of the metabolic pathways because they're common to both carbohydrate and fat metabolism. So that would include the Krebs cycle and the electron transport chain. So they're used in carbohydrate, fat, and protein metabolism. So with fat metabolism, there's one additional pathway to tack onto that, and that pathway is called beta oxidation, and I'll be covering that during this lecture. So beta oxidation comes before the Krebs cycle, and then you get the electron transport chain. So some review questions for you. What type of carbohydrate is best to consume before exercise for stimulating fat oxidation? The correct answer to this would be A, low glycemic index carbohydrates. So low glycemic index carbohydrates result in a slow and small increase in glucose in your blood, whereas high glycemic index carbohydrates result in a fast increase in glucose and a higher increase in glucose. That greater increase in glucose will result in more insulin being released into your blood from the pancreas, and insulin will inhibit your fat oxidation. So if you can consume a low glycemic index carbohydrate before exercise, it's better for stimulating fat oxidation because it will result in a lower insulin release, and insulin has an inhibitory effect on fat oxidation. So you get less of an inhibition of fat oxidation if you can consume a low glycemic index carbohydrate before exercise. And I went over some examples of low and high glycemic index carbohydrates last class. So I put up a table last lecture that showed you some foods that were different. Which type of diabetes can be substantially alleviated with increased physical activity? The correct answer to this one is B, type 2 diabetes. So type 2 diabetes is the result, most cases it's because of obesity caused by poor diet and lack of physical activity. So to a large degree, it can be reversed with an increase in physical activity. Type 1 diabetes cannot be reversed, but exercise is still highly recommended for type 1 diabetics because they are at an increased risk of cardiovascular disease. And if you're physically active, that will reduce your risk factors for cardiovascular disease. So type 2 diabetes can largely be reversed with physical activity. Type 1 diabetes cannot be reversed, but you can still prevent a lot of the cardiovascular disease risk factors that might be elevated with type 1 diabetes. So your best answer here would be B, type 2 diabetes. Now I'm going to get into our new section. So this is lipid or fat metabolism. And a few questions here to kind of lead you into this section. So some of this is review. Which of the following hormones would stimulate fat storage? So your options here are cortisol, epinephrine, insulin, or all of the above. The correct answer is C, insulin. So insulin tends to pack things away, including fats, into adipose tissue. Cortisol and epinephrine are both released during exercise, and that will result in the breakdown of fat from adipose tissue. So your best answer here is insulin. Which metabolic pathways are not involved in fat metabolism? So your options here are glycolysis, Krebs cycle, electron transport chain, or all of the above. The correct answer here is glycolysis. So glycolysis is strictly used for carbohydrate metabolism. Krebs cycle and electron transport chain are pathways that are common to both carbohydrate and fat breakdown. So that would involve the aerobic breakdown of either fats or carbohydrates. The Krebs cycle and electron transport chain are both in the mitochondria. Which metabolite is common to carbohydrate and fat metabolism? Your correct answer here would be C, acetyl-CoA. So acetyl-CoA is the entry point to the Krebs cycle. Fatty acids, glucose, and protein can all eventually be broken down to acetyl-CoA. Pyruvate and lactate are metabolites of carbohydrate metabolism. Acetyl-CoA is common to fat, carbohydrate, and also protein metabolism. So acetyl-CoA is the entry point for pretty much all your substrates. Anything you eat from your diet can eventually make its way to acetyl-CoA. That would be in the mitochondria, and that's the entry point for the Krebs cycle. So again, the answer here is C, acetyl-CoA. Storage of fat. Fats are stored in the form of what are called triglycerides. They're called triglycerides because they're made up of 3 fatty acids. And then the glyceride part of that term comes from glycerol. So glycerol is a carbon backbone. And I've kind of drawn a rough diagram of a triglyceride here. You've got the 3 fatty acids just represented by Fa, and they're all bound together in this 3 carbon backbone. So each of these points here would represent 1 carbon in your glycerol molecule. So when you break down fats, when you break down triglycerides, you're going to be breaking off these fatty acids, and you're going to end up having fatty acids and glycerol that appear in your blood from your adipose tissue. So glycerol, as I mentioned, is a carbon backbone. It can be made from glucose. So glucose can be taken up into your adipose tissue and converted to glycerol. And it can also be made into glucose through that pathway of gluconeogenesis in the liver. So you recall during exercise, when you break down fats from adipose tissue, you get formation of free fatty acids in the blood plus glycerol. The glycerol can go to the liver and be made into glucose through the process of gluconeogenesis. So that process would be very active during exercise. Fats are mainly stored in adipose tissue. They can also be stored as triglycerides in the muscle and liver, and they're very large molecules, so they can provide a lot of energy. So it's the type of energy source that your body relies on if it's doing long duration aerobic exercise. So some questions to think about here. If fats supply more energy than glucose, then which molecule has a greater size and a greater number of carbon bonds, glucose or fatty acids? So the correct answer here would be fatty acids. So when you break down those carbon bonds, you can get energy from that. You can make ATP, so you get a lot more ATP made from the breakdown of fatty acids compared to the breakdown of glucose. Which molecule takes longer to metabolize? The correct answer here would be fatty acids. Just because they're bigger, they have to go through an extra metabolic pathway in the mitochondria to be broken down. And so that's just going to take longer to break down because they're bigger. And which one would be used during short duration, high power exercise? The correct answer here is glucose. So if you need energy quickly, your body and your muscles prefer to use glucose as a fuel source. Because it's a smaller molecule, it can be broken down immediately through glycolysis. It's a fast metabolic pathway, it's short, and you can get ATP quickly from the breakdown of glucose. It takes a lot longer if you're breaking down a fatty acid. You'll hear the term unsaturated and saturated fatty acids. So fatty acids are made up of long chains of carbon. So I haven't drawn the complete chemical structure of a fatty acid here, but I've just drawn, in this case, the carbon chains. You can see the carbons bind with hydrogens. So when a fatty acid is said to be saturated, it means that all the carbons are bound with the maximal amount of hydrogens that it can be bound with. So it's said that the carbons are saturated with hydrogen atoms. And these saturated fats, they're usually solid at room temperature. So it would be, for example, butter. It would be your animal fats. So, the fat that you cut off from your steak. the fat that you see in the skin of chicken. Those would all be classified as saturated fats. They're solid at room temperature. Unsaturated fats. Unsaturated means that you've lost some of the hydrogens from the carbons. So there's less hydrogens, some of them are gone. And because the hydrogens are gone, if you know your biochemistry, you'll know that there's going to be a double bond formed between the carbons here. Unsaturated fats have double bonds. If they have a single double bond, then it's called a monounsaturated fat. If they have multiple double bonds, then it's a polyunsaturated fat. These fats are considered healthier in your diet, and they're the ones that are usually liquid at room temperature. So that would include things like olive oil, it would include canola oil, sunflower oil, things like that. So they're liquid at room temperature. Now I'm trying to give you some practical application to fat metabolism here. So once you break down triglycerides from your adipose tissue, you get glycerol and fatty acids that go into the blood. The glycerol can make its way to the liver to be converted to glucose. Fatty acids make its way across the muscle fiber membrane. Eventually they enter the mitochondria, where they can be oxidized and broken down further for energy. When they cross the mitochondrial membrane, there's an important enzyme here that you don't have to know for the course, called CPT, or carnitine palmitoyltransferase. Again, you don't have to know that enzyme, but in that conjunction with that enzyme, there's a molecule called carnitine that helps to carry the fatty acid across the mitochondrial membrane. So I mentioned this just again to give a practical application to all of this. Because if you go to nutritional supplement stores, you'll see sometimes they'll sell carnitine supplements, and these carnitine supplements are promoted as a weight loss or fat loss supplement. So this is kind of the biochemistry behind the idea of the carnitine as a weight loss supplement, and that they allow improvement of, they help fatty acids to be transported across the mitochondrial membrane, where the fatty acids can then be broken down. So theoretically, carnitine would help with that process. Now, studies with carnitine supplementation are quite mixed. So there's some studies that show that it's effective in some people, and then some studies show that it's not effective for weight loss or for fat loss. So it might not be effective because if you're taking carnitine as a supplement, first it has to get past the muscle membrane, and then it has to get incorporated into the mitochondrial membrane, so there might be some trouble doing that. Another factor too is once carnitine helps with the transport of fatty acids across the membrane, it gets recycled and it goes back and participates in that process again. So carnitine isn't really used up that much in this process because it is recycled. So that might be a reason why sometimes carnitine supplementation does not work. So this is a bit of a review. What aerobic metabolic pathways are common to carbohydrate and fat metabolism? And you can also say protein metabolism. So this would be the aerobic breakdown of carbohydrates or fats. The answer here is the Krebs cycle and the electron transport chain. So I've just drawn a schematic of your mitochondria here. The Krebs cycle, electron transport chain are inside the mitochondria. You can have pyruvate, lactate from carbohydrate metabolism, fatty acids from breakdown of fats, amino acids from the breakdown of protein. They can all enter the Krebs cycle through acetyl-CoA. And again, important parts of the Krebs cycle are that it produces 3 NADH, 1 FADH per round of the Krebs cycle. Those can go to the electron transport chain. The NADH can be will result in 3 ATPs being produced here. FADH will result in 2 ATPs being produced in the electron transport chain. So that's 3 ATPs per NADH molecule, 2 ATPs per FADH molecule. Which of the following enzymes is not involved in fat metabolism? The correct answer here would be your pyruvate dehydrogenase. So that's involved in just your carbohydrate metabolism. So the pyruvate dehydrogenase is involved in taking pyruvate and converting it to acetyl-CoA. So it's outside of the Krebs cycle and it's just involved in carbohydrate metabolism. Succinate dehydrogenase and citrate synthase are both enzymes of the Krebs cycle, and cytochrome oxidase is an enzyme of the electron transport chain. So these three are involved in fat metabolism. Since fat metabolism involves the Krebs cycle and the electron transport chain, but pyruvate dehydrogenase is unique to carbohydrate aerobic metabolism. So the answer here is A. It's the only enzyme not involved in fat metabolism. Now I mentioned that fatty acids, they go through the Krebs cycle and the electron transport chain, but they're very large molecules. They involve these long carbon chains. Those carbon chains have to be initially chopped up through a different metabolic pathway called beta oxidation, and this occurs before the Krebs cycle. So I've added to this schematic just for fatty acids. So in the other one, I just had fatty acids that had an arrow to acetyl-CoA. In reality, the fatty acids first go through this beta oxidation before they go to acetyl-CoA. It's called beta oxidation because beta corresponds to the second carbon in a long chain of carbons in your fatty acids, and it chops your carbon chain in your fatty acid down two at a time. So it goes through this beta oxidation multiple times, chopping the carbons by two at a time. Those two carbon molecules then form acetyl-CoA. So recall acetyl-CoA is a two carbon molecule, and then the acetyl-CoA goes through the Krebs cycle. So you can imagine a fatty acid that's a very long chain. You're chopping it down two carbons at a time. You'll get multiple acetyl-CoAs formed, and this Krebs cycle will spin through multiple times when you break down a fatty acid. So you get one NADH and one FADH from each round of beta oxidation. So each of those can go to the electron transport chain and produce ATP. And then you get these multiple rounds of Krebs cycle where you get 3 NADHs and 1 FADH per round, again going to the electron transport chain to produce ATP. So from one breakdown of one fatty acid, you can get quite a high number of ATP through that process, quite a bit more than one molecule of glucose. So this is just to kind of review beta oxidation. So you have these long carbon chains that are part of a fatty acid. And as I mentioned, beta oxidation is called beta oxidation because you are chopping, the first carbon in the chain is called the alpha carbon. The second is your beta carbon, and you're chopping the carbon chain down two at a time. So each time you go through beta oxidation, you're chopping off two carbons. So it's always the beta carbon that's chopped off, the second carbon in that chain. So beta oxidation, this is a summary from that diagram. The fatty acid is broken down two carbons at a time. Each of those two carbon molecules will form an acetyl-CoA, which then goes through the Krebs cycle. And another enzyme I'm going to have you know or recognize is called hydroxyacyl-CoA dehydrogenase. Quite a long name for an enzyme, but it's often used as a marker of beta oxidation. So it's an enzyme that's in that beta oxidation pathway. It's one that's easy to measure in a biochemistry lab, and so that's often used to assess the capacity of that pathway. So it's a mitochondrial protein, a mitochondrial enzyme, because beta oxidation occurs in your mitochondria. So question here is, how many rounds of beta oxidation are required to break down an 18 carbon fatty acid? So recall that it's broken down two carbons at a time. Now you think the answer would be 9, but the answer is not 9. And I'll quickly illustrate this on the whiteboard and how you can get the correct answer from this. So on the whiteboard, I'm going to draw 18 carbons that are in that 18 carbon fatty acid. So there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you've got your 18 carbon fatty acid. With beta oxidation, it's broken down 2 carbons at a time. So you get one round there of beta oxidation, another round of beta oxidation, and so on. So your beta oxidation breaks it down 2 carbons at a time. So now if you count the number of rounds of beta oxidation that are represented by these individual lines that are slashing by 2 carbons at a time, you will get 1, 2, 3, 4, 5, 6, 7, 8 rounds of beta oxidation. So for an 18 carbon fatty acid, it ends up being 8 rounds. And the reason it's 8 rounds and not 9 is that in the end, you have 2 carbons that are left over. Now, each of these 2 carbons from this 18 carbon fatty acid will form acetyl-CoA. So all of these will eventually form acetyl-CoA. So you get multiple acetyl-CoAs. In this case, you're going to have 9 acetyl-CoAs. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the Krebs cycle in this case goes around 9 times. So each round of the Krebs cycle, you're producing 3 NADHs, 1 FADH. They all go to the electron transport chain. For each NADH, you get 3 ATPs produced in the electron transport chain. For each FADH, it's 2 ATPs. And then recall that with each round of beta oxidation, you also get 1 NADH and 1 FADH that are produced, and those can also go to the electron transport chain. So if you do the math, with an 18 carbon fatty acid, you're going to have well over 100 ATPs that are produced from the breakdown of that fatty acid. Whereas with glucose, recall that you only had 36 ATPs that were produced with the breakdown of a glucose aerobically. So the correct answer to this question is 8. Now the last few slides, I'm just going to go over a few pointers on fat digestion and what happens to fat metabolism after you've consumed fats in the diet. So after being taken up from the digestive tract, triglycerides are packaged into chylomicrons. So triglycerides are not very soluble in water, so to be transported in blood, they get packaged in these chylomicrons that allow better transport of fats in the blood. The liver can take up the chylomicrons and repackage the triglycerides into lipoproteins, and then those lipoproteins can deliver the triglycerides to, for example, adipose tissue for fat storage. So you've probably heard of different types of lipoproteins in your blood. Some are healthier than others. The question here is, what is denser, fat or protein, and who would sink easier, a fat person or a muscular person? So if you're a muscular person, you'll notice that when you go swimming, if you have a lot of muscle mass, it's easy for you to sink if you stay still in the water, whereas a person with a greater amount of body fat will tend to float. It's because fat is less dense than muscle, and so protein is more dense than fat. So the other question here is, what molecule contains more triglyceride, your low density lipoprotein or your high density lipoprotein? The correct one is the lipoprotein that has a lower density, because triglyceride is fat, and so if you have greater amount of fat in the lipoprotein, it's going to have low density. So your lipoproteins are made up of triglycerides, cholesterol, and proteins. Low density lipoproteins have high fat content or high triglyceride content. That's what gives them a low density. The high density lipoproteins have a low triglyceride content, and that's what makes them lower in density. So this diagram shows you what happens with once you've digested fats and how they can be taken up to the liver and then distributed to adipose tissue. So I've got glucose.